So I've been writing on a language of my own for the past 3 years, sort of in my spare time. And I want to tell you about it. Those of you I've already talked to know that I very much want to tell you about it, and now you can no longer escape. So let's do it. So first of all, I've given you build instructions and download links on the front page. I strongly encourage you to take advantage of those, though I cannot sadly literally force you to. To emphasize this, I've also put a link to a download page on the top right, and it's going to remain on the top right for the remainder of the talk. Now, you may be asking a reasonable question here, which is, how do I use this clicker? That's not the question. You may be asking a reasonable question, is why exactly are you doing this at DConf? This is DConf, this is not NeetConf. Is it like a rule where if you hold 3 D talks, they give you a free talk on the subject of your choice? No, I believe you will find, if you look at an actual sample code, a sample, that Neat is heavily inspired by D. This style of code should look pretty familiar. Oh, does it say blatant ripoff? Sorry about that. Heavily inspired by D. And this style of code should be pretty familiar, which is why mess with a good thing, right? So I have several goals here, which is that Neat is, to some extent, trying to demonstrate features that I wish were in the D compiler. So we've had some disagreements about that, like things that I think are important and that other people think is less important. And I think if you see them running in a complete environment, there's a higher likelihood for you to agree with me. Furthermore, DMD itself is 20 years old, and while it is relatively speaking fast compared to C++, for instance, it is also very idiosyncratic. It is not native D code in that sense, for very good reasons, I understand, but nonetheless, it may be helpful to have a compiler that was written from the start to be, not exactly to be readable, but that maybe has a better chance of attracting contributors. Also because I enjoy writing compilers. So, what is this language like? Neat is, as the classic schema goes, a moderately verbose, ref-counted, statically typed, single-dispatch, object-oriented language with multiple interface inheritance and single-class inheritance, and I will not even try to loudly herald its novelty. There's a lot of things here where, frankly speaking, D has already done things in the best way I can imagine, and I'm not just saying that because I've been coding in D for so long, trust me. So why would I mess with it? So in most things where I didn't have a strong opinion on the topic, I have done things the way that D has done them. There are some things that are diverged that you will run into pretty quickly, which is the first one, that variables are immutable by default. That is not to say immutable in the D sense, but immutable in the sort of C++ sense, in that you cannot change the actual value of the variable. The idea of that is that you look at a function, you see a variable, you shouldn't have to think about where its value changed 20 lines down. Objects are non-nullable by default. Nullable is kind of a weird state. It's just more to do with pointer management than to do with object orientation. So by default, if you just declare a class, you get a class that null cannot be cast to. All of these can be modified. You can write nullable class. You can write mutable variables. It's just intended to be the default case so that it looks at least a little weird when you diverge from it. We have an LLVM backend. We also have a C backend. Having a C backend is very valuable because you can use it to bootstrap the compiler. So you just compile it with itself, and then you save the C sources, and you just put them in a zip file, put the zipper on GitHub, and then anyone with a C compiler can get your compiler back out, which is also the thing that lets you use the standard library in your compiler because it just gets compiled into C objects effectively. LLVM, of course, if you want something slightly speedier. So, of course, you're paying for the speedier code by having to use the LLVM backend. LLVM is very much a bane, and it's a present, and it is also a curse for compiler developments. Because, like, there go your milliseconds. Compared to D, the type system is a lot more freeform. In D, you have like classes, you have structs, and you have alias. And of course, the built-in types. Neat extends that with tuples, with sumtypes, with identifier types, which I will get to. And the idea of it is that a lot of the time, the overhead of a struct is excessive. Like, you don't want to go off and write your separate type if you just want to return two values. Due to the presence of macros, by the way, I have proper macros. It should be a lot easier to embed domain-specific languages for specific use cases in the code. And I have to say that compared to D, which has been growing for 20 years, there's a lot less depth of functionality. I think at this point it's a complete language, but it's very much possible at any step that a required feature just isn't going to be there. The standard library is, of course, anemic, and you're generally going to have to, if you want something to be running, you're going to have to do your own background work for that. Yeah, let me talk about macros for a bit, because I'm very hype about them. Macros are sort of a complete replacement of what CTFE is doing in D. With CTFE, you have this entire separate layer of execution where you're running the optimizer and you're effectively turning it into a very weird JIT. So since we already have a compiler backend, instead of doing this weird JIT, we just have the ability to take code in the compiler and load it back into the compiler and run it at compile time at native speeds with the exact same hardware that, with compiler hardware, sorry, with the exact same software that every other part of the compiler uses. So am I trying to replace D here? Am I here purely as a parasite? No, absolutely not. For one, just the depth of features of a mature language like D is going to kill you if you try to replace it. There's so much stuff in D. Like every time I was writing Neat in the early, even after 2 years, I was like, hang on, I need this thing. Hang on, I need that thing. I need that thing. I need that thing. There were very many of those. And so no, I'm not trying to replace D. I'm trying to offer one alternative design philosophy. Also, it is very much a sibling language. You can use a D syntax highlighter and probably get pretty good results on Neat, but Neat code is not going to run one-on-one on a D compiler. D code is not going to run one-on-one on a Neat compiler. But since they still look relatively similar, I think it should be very possible to demo ideas for D using Neat as a platform. So since I'm not trying to purely parasitize the user base here, I have these slides called what should D copy from Neat? And I'm going to go into all of these more. Macros, I know it's not going to happen. I have to say it every time because I still think it's true. Lambdas, we'll go into all of these. We'll get to it. And about ref counting. But let me show you something shiny. This is list comprehensions. If you've done some Python, you will recognize these. The idea is that pretty much for everyone, you can just read it left to right and have an idea for what it does. For instance, give me the first I for I, A in the sense of index element in array, where the condition FA holds, else return the value -1. If you've written a compiler, yeah, I had these before I had for each loops. Literally. The macros give you an unprecedented power to add powerful features to your compiler very early in. And it's just purely enjoyable. Right, let's go into the first of what I think DMD should copy from my approach. Now, DMD as a compiler is extremely fast if you're used to other languages. It achieves that in part by using heavy mutation of state. It just allocates a lot of stuff up front, and then it does changes to that state in various passes. This is a good design approach for a 20-year-old computer. The problem is nowadays we have 20 or 30 threads, and then it begins to kick you a little because you have a lot of synchronization requirements between parts of the compiler. And every time you modify state, you also invalidate the previous state. And if you were trying to hang on to that, now you need to make a lot of copies, and now it starts to get a bit problematic again. The thing is, if you write a compiler that is perfectly optimized for a 20-year-old computer, then it's going to be insanely fast on a modern computer no matter what you do, because thanks Gordon Moore. But specifically, the way templates in CTFE works, I think, could benefit from a different approach. Now, I'm just going to show you how it works in my compiler. So you have a syntax tree, and the syntax tree is immutably transformed into an intermediate representation, which should probably be an intermediate static single assignment form, but sadly isn't. And that intermediate representation is then again transformed without any mutation into the backend SSA form. The important thing here is that the previous state of each operation is never changed. The abstract syntax tree is never mutated, and after it's been created, the intermediate representation is also never mutated. The advantage, there are some parts of that where I do mutate, and it's good to have backdoors, but broadly, this is what happens. Result, if you know how templates work in D, every time you instantiate a template, you make a copy of the syntax tree, of the tree of the template, even if you're only affecting a small part of it. that never needs to happen. The intermediate representation can be very minimal. If you're working with static if, static for each, you're making a lot of clones. You may be cloning code that is never even going to have semantic routines called on it. None of that is necessary if you just go directly from AST to your AIR. Everything can be cached. Nothing that has ever been valid is going to become invalid after in a different compiled step. And most importantly, you can run as many threads as you like on your compilation simultaneously. Right, I'm going to show this off, actually. I think you kind of need to see this in action. So I'm going to tell you about it first. So I do make heavy use of this in the compiler. We have several layers of caches. Since we're using LLVM, we need to have several layers of caches. For instance, objects are all cached on disk because otherwise it would be very painful. So the problem is every time you rerun the compiler binary, in a classic setup, you run GCC source code, get object code out. And you load a lot of modules into memory, and you build a nice little module cache, and then you delete it again. And then if you do it again, you build the module cache, and you delete it again. So that's kind of painful. So what if you just don't rerun the binary? You just rerun the compile. I'm going to show this to you, actually. So I have this demo called Dragon, which is a dragon curve. Hang on a second. Build folder into the path. Oh yeah, I can just look ahead. I'm going to time this. Okay, it's decent. However, we had an object cache that was hot. I'm going to delete that. And so that's what you get with pure LLVM and for everything, so that's a bit painful. You don't want to see that. If you rerun it, now it's nice and cached. Now it's warm. And I'm going to take out linking just as an experiment, so that makes it a lot better. A lot of that is really just the final linking step. Let me just run this as a demo. Yeah, by the way, Raylib support. So it's a dragon curve. Yay. You like that. OK. But what if I want to make a change to it? So I'm going to run this in a special mode, in the compiler in special mode, which is neat, loop, watch, run, dragon. OK, that comes up. And so now I've quit the program, and I'm going to change the writing on the button to plus, plus, and minus, minus. I want you to watch the terminal window in the back when I hit save. And yeah, no, they changed. And you can see that running the program took longer than it did to recompile it. Like just getting Raylib to come up to its startup function took longer than the actual complete compiled it. And most of the time on that is spent running the linker. So if you get a faster linker in that, it's going to go down to sub 100 milliseconds, probably sub 50. So that's the sort of benefit you get. I could also have turned on threading, but in a small program like that, it doesn't do much. All right, back to the talk. Let's talk about the type system a bit. I've promised you tuples, so we have tuples. We also have tuples with names on it. These names are not just decorative, they are part of the type system. So in the example of latitude and longitude, you could not implicitly pass this tuple, even if it was the right types otherwise, to a function that would take longitude and latitude. You would have to form a new tuple with the right names. We have sumtypes. So like standard sumtype, the difference is that it's a bit better integrated. I will go into that. So if you have a sumtype that is declared as consisting of the types A or B, like in OR sense, then to access this, you have to split it up sort of into two bundles, into the A bundle and in the B bundle. And then each of those expressions gets put together again into a new sumtype. Those don't have to be the same types as before. We can get a new sumtype out. We have identified types. Those are kind of cute. So like if I write colon A, this is simultaneously a type and a value, and it's the type of which the only value is colon A. This is useful if you're doing ad hoc sumtypes, and this is 0 bytes, by the way, in memory. And so if you're doing this, it just tells you decoratively that if you write parenthesis colon pos comma 5, this is the pos half of the sumtype. Yeah?
Sorry, one question. Could you go back to the demo you just showed? You said it's heavily cached.
Yeah.
When you run it in loop mode, is it still cached on the disk, or is it cached?
Yep.
Is it cached in RAM? Because I guess that might just be a tiny bit faster. So which one is it?
It's still cached everywhere. This is just a mode in the compile driver.
Okay, so it's like when the mode is in the compile driver, it is cached in memory.
No, hang on. To clarify, we are always cached in memory, anyways. Because if you're doing module imports, then if you import module A on this side and you import module A via a different path somewhere else, then you still want to be caching. So we always have cache in memory. The loop mode just prevents that cache from being deleted at the end of the compile step.
Okay, cool, thanks.
No problem. Right. So it's sumtypes. You think this is cute, but it's not really important. It is important. Because sumtypes let you get away from a language design perspective with a lot of things. For instance, if you have an array literal, in D it's pretty easy to get errors here because you're using two incompatible types of elements in the array. In init, it just says, okay, you're trying to put an integer and a string into the same array, whatever. This is now an array of integer or string, which is very logical. So this actually comes up, this sort of merging process comes up in a lot of parts in the compiler, and it is very handy at any point to be able to say, okay, we're going to merge it to a defined type, which is the sum type. Okay, here's a trick question. What is the type of return 5? Ideas? Yeah? Bottom, very good, very good. So now naively you would think this would be int. It is not int, because return is a non-local exit. At this point we have left the function, so if we treat return as a value, then the type of return is no return, because you cannot actually get to the value because you're already gone from the function. That sounds stupid. It just sounds like a stupid trick. It has consequences. I will come to them. Now, this slide is redundant. Okay. Because it interacts with the case expression in a very fun way. For instance, if we have foo, and we have foo declared to return a value of foo or an error, as one may want to do. Now, we want to get rid of this error. We don't want to do a go where we just check for error, and if error, then return error. We just want to be done with it quickly. And what we can do is we can chain this sum type into a case expression, and the case expression lets you get away with not listing a type that's in the sum type. In that case, it's just passed through as identity. So in the foo case, this case expression just passes through as identity. In the error case, we return from the entire function. We don't return from case, we return globally. And because return is of type bottom, it drops out of the sum type, because the merge of bottom and any other type is that other type. So what's left over at the end is just foo. Isn't that cute? I think that's cute. Now, you can actually do the same thing with nullable classes. We have a function that returns a nullable class, and you just call the function, and you take the null part, and you replace it with bottom, and it's gone from the type. It's just foo left. This is internally because nullable foo is actually a thin layer above foo or null pointer. That was a lie. I wish I'd done it that way. Unfortunately, I only added sumtypes pretty late in. What it actually is a clever hack in the case expression, but we could probably do it that way, and we probably should. That would be cool. Right, the problem, if you're looking at the D side, D is a lot more flexible here because D does not have several separate types for non-nullable types. And the reason you could not do it this way in neat is because if you check if the result is null, return null, then afterwards the result is still going to be nullable. By getting rid of the error types directly on the call, you get a variable that is immediately of the correct type. And also you can't do this in D because you can't return out of match, which is another advantage of a native implementation. By the way, going back a bit, in the error case, this case error return, if you think of this as case error return error, then this is just done by foo parenthesis parenthesis question mark, by the way, which lets you do error propagation very easily, but it's just the same thing as that. All right, let's change the topic. One thing I really think D should copy from neat is that neat has packages and D doesn't. And this is going to be a bit of a stretch, I admit, because we've been taught that D has packages, right? This package is just something that modules is in. These packages are cosmetic. A package in D is just a folder, effectively. The thing is that in neat, a package is a defined object. So if you use the build system, if you use package dependencies like you would in dub in D, in neat, you actually get those as primitive units. Something very cheeky you can do in D is you can write a dub package that imports a module from your regular compile. And then you run into difficulties because the way in which you're building this program is going to determine what actually happens there. If you do a static if compiles check via a module from your main program and you're doing dub in isolation, you're doing the dub build in isolation, you're going to see that module. And once you access that module for a second time during the main build, you're not going to see the module. Once you access it for a second time, it's going to be there. So you get divergence between different compiles depending on how you run the compiler. And that also means that in D, you actually cannot pre-compile dub packages unless you capture D flags, unless you look at the complete include graph. Another benefit of that is that you actually get static checking of these import requirements. If you have init a package file and you depend on another package, then you literally can only import packages from that other package. It's non-transitive. If you want a transitive dependency init, you have to declare it in your package file. You have to say, I want this package that another package also uses. So it's a lot more direct. In that way, you cannot accidentally import a module, which is important because in D, if you have multiple modules with the same name, it's, I think, pretty random which one you get. Another interesting benefit of that is that, and I don't support this at this point, but I'm probably going to support it in the future. If you have deprecations, if you have behavioral changes where you want to support the old version and the new version, you can attach this to the package. You can attach this to the package configuration. And imagine you could say in your dub.json, I don't want, I always want bounce access or bounce checking to be left in, or I always want bounce checking to be left out, and have it be honored by dub, even in a compile run that pulls together several different packages. And you could still have those all interacting all with their own configuration decided by the author. Well, with packages you can. Here's another thing that D should copy. Lambdas in D are dreadfully clever. If you're passing a lambda to a function as a template parameter, what this actually does is, so if you're passing a lambda to map, for instance, it lifts map into the same level of stack as your lambda, into the same scope, and then it's allowed to call the lambda as a sibling function. When I realized that was how it worked, I was struck by its cleverness. It's amazing, it's clever, it's simple. You don't need to worry about lifetimes. The problem is, of course, it completely falls over when you have a function that takes more than one lambda, or that takes a lambda in some other context, which is, by the way, why to this day in D, you cannot have a method on a struct that takes a lambda alias parameter. Because the struct is already its context, it can't be moved somewhere else. There were attempts to change that with multi-contexts. I think Ian rioted. And so we're not getting, I very much understand that it's complicated. The thing is, all this difficulty goes away if you just treat lambdas as values, like C++ does. So a lambda in init is just a variable. You can stick it in a variable. You have to use auto because the type is very much internal. You cannot declare the type of a lambda. So you can only do it with type inference. So what this does is just the stack pointer of the function. It's just a pointer to the stack frame. It's exactly as performant as it is in D, because one way or another you're passing the stack frame to the function. You're just doing it explicitly versus implicitly. And you can pass as many as you like. You can pass 2, you can pass 3. The ref counting is terrible. The ref counting for those is, ask me about lambda quarantining at DConf. I have stories. But they work. And they could easily work in D. We just need to drop the exclamation marks on every standard algorithm call. Oh yeah, D should copy reference counting, is what I would say if I was insane. Reference counting was a horrible mistake. Walter is 100% right about garbage collection. The thing is that if you're writing your own language, adding garbage collection is just LD preload is uselib. I mean, you can write your own garbage collector if you want, but you can also not bother. You can just be like, whatever, preload boom. I want to be very fancy, so I'm going to call gc malloc gc free. It's easy. Adding reference counting to init is easily responsible for half the lines of code in the compiler. It's the single most subsystem that takes up the most effort, that has the most bugs. Doing it even halfway effectively practically forces you to use immutable variables. On the other hand side, you finally have a reason to use immutable variables, so that's good. Why does it force you into immutable variables? I mean, let's look at this example. You have an object variable. You want to pass it to a function. Maybe we can optimize this. Maybe you can say, well, it's a variable. It's going to live for the entire lifetime of that function. Maybe we don't need to take a reference when we're passing it to that other function, because that function is going to return, and then we're just going to free the original. It's fine, right? Should work. Doesn't work, because you can just override that variable, and now your parameter is invalid, because you've dropped the last reference to the object. Right, but init this wouldn't compile, because object is not mutable. And if you declare this mutable, you are affirming that you're okay with a bit of speed loss in order to get that convenience. Right, let's talk about macros for a bit. I'm really happy about macros. The thing about macros is if you're writing your own language, then if you're adding a macro system, if you're adding like import C, then you need to write the C compiler. If you're adding, I don't know, list comprehensions, or you need to maintain the list comprehensions module. If someone comes to you and you have macros, you've added macros, and says, I want to have so-and-so in the language, you can just be like, okay, fine, go write it. You can write it. You can just go and do it on GitHub. You can import it from GitHub. If there's a built-in macro, if there's a macro that's shipped with a compiler and it doesn't work right, you just fork it. You just make your own copy of it. And it's on exactly this, it has parity. A downside of that is that your compiler internals are now a public API. This may not be something you want. On the other hand side, if you design your compiler so that this is something that makes you proud instead of makes you wince, then the rest of your compiler is also going to benefit from that. It's a huge incentive for clean internal design. Okay, probably the last thing I want to show you. There's all sorts of macros in need. You know CTFE. You just have to imagine, like, if the compiler lets you take a CTFE function and let you run it as a hook. With compiler, with DMD as a library also being CTFE'd, and like passing DMD internal classes to that hook function and getting the result out and sort of mixing it in, then you know how macros work. So instead, I'm going to explain to you how quasiquoting works, which is strongly associated with macros, but it's probably, if you're writing your own compiler, this is the thing you want to pay attention to. For instance, considering we have this list comprehension, we want to apply the function foo to every A in the array. I'm going to declare at this point that foo returns void, so we don't need to worry about forming a new array because that's really going to get too complicated. We just want to run foo. We want to call foo on every member. And we don't have for each loops, we just have for loops, which was the place where I started out at. Right, let's look at this. We have parsed the syntax. We have split it into 3 halves. We have split it into the body expression, we have the iterator variable, and we have the source expression. Now, the traditional way to do this, if you're writing compilers, is you're going to build a syntax tree manually. You're going to have a for loop over a variable. You're going to initialize the variable to 0. Your variable step is to check that it's the identifier, which you've just declared for the for loop, is smaller than the length of the source expression. You can tell, by the way, maybe that I've decided to use a more narrow font for the traditional way. And this should fill you with doom. All right, let's continue. So the for loop step is you assign to the loop variable I incremented by 1. So far, so clear. Now, the body is a bit more interesting because you need now to declare a variable with the name A. So you do a variable declaration with your iter, and you assign to it the array index operation of the source expression with the identifier I, and then you just insert the body. Yeah, simple, right? It's a bit complicated, but it's still viable. There's a trap in here, which is those of you experienced with compilers who have spotted it. The actual correct way, this is wrong. This is completely wrong. The correct way to do it is like this. Because what we've done is we've double evaluated the array source. And that's fine in this case because it's a variable, but it could have been a function. And then we would have called that function like n+1 times. And so we just actually need to stick that variable, that source into its own variable. And then we need to reference that variable every time we want to use source. And it's just become this huge blob of code that nobody understands. All right, and now like a magician, I'm going to show you how to do it with quasiquoting. Look at that. Isn't that pretty? And the thing is that the thing on the left and the thing on the right produce the exact same AST, the exact same compiler data structure. The thing that this thing on the left is easily expressed by just writing the code and interpolating your variables, your syntax trees at certain points. So I just do auto source is the interpolated variable from the outside, which is called source. And this is exactly the same as writing a variable declaration node with the name source and that parameter. The dollar means that it gets interpolated in during evaluation, effectively. And this has a lot of benefits. The one benefit is that it makes compiler development easy, because you can define this small core language, and then you can just use it again, use it again, use it again. And you can build up your internal compiler primitives in terms of the previously defined primitives. There's a really cool side effect also to this, which is that if you're making a mistake in your quasi-quoting, if you have a runtime error, the runtime error is going to have a line number that points you at the exact code where the error happened, even if that error is in the compiler itself. So you can, during development, you really want this, because you're going to have a lot of bugs in the metacode that you write, and this way you can attribute it directly to a source code line. There's a bit of a risk here, which is that if you start out working like this, you start out appending to an array. I'll do quasi-quoting. I'm going to, for instance, do lifetime accounting. I use quasi-quoting for that. I'm going to write an element to a hash table, quasi-quoting. Well, I need to increment the reference count. Well, I'll use quasi-quoting to do the reference count incrementing code. And before long, you end up with what you're not seeing here is that this is not like functions. This gets inlined every time. The code that you write just gets dumped with modifications in every single spot that you're using that feature in. So you can end up with very innocuous-looking code that generates like megabytes of executable. The thing is, you can still take advantage of quasi-quoting even if you hide it in a runtime function. And then you really get the benefits of both. So just a brief note, how does this work? Well, what we're doing is actually very easy. We're running the compiler, and we're trying to generate a quasi-quoted symbol. So what we're doing is we're passing this entire block, just normally passing it, and then we get a pass tree, and we throw it away. But we remember what the code was that we passed. And the code that we actually emit here is just, we take that code, we put it in string literal, and then at runtime, we just pass it again. I mean, the compiler is a library, right? You can just do it again. And so you get an instant syntax tree at runtime. There's a more complicated way to do that, where you just use manual quoting. You don't want to do that. Talk to me about it at DConf. I did painful things in the compiler to support this before I realized I could just pass it twice. Okay, finally, I want to show off something pretty to end on. Look at this JSON value code. This is the D version. Right, this is, if you're writing encoders, decoders, this comes up a lot, right? And you return a JSON value, and it takes a constructor parameter, and so you need to give it an array of JSON values. So everything in here, a hash of JSON values, everything here needs to be valid for the hashing, because you're not forming a JSON value, you're forming a D type. So you want to do version goes to JSON value of version, data goes to JSON value of an array of JSON values of data, and you need to repeat yourself a lot. But if you have macros, you can do this very prettily. And this actually invokes the JSON parser internally. Like, the source code is passed as neat until it reaches that opening parenthesis, and from that point on, it's literally passed as JSON. Until it reaches an expression that it can't pass, and then it goes back to neat. And so you can literally you're literally writing a JSON object. If you put a comma after the data line, it would be a syntax error. And you can freely interpolate, you can do function calls, you can do anything in there. Isn't that cute? I think that's neat. All right, those of you who want to design languages, some hints. You will sometimes read on Stack Overflow that C is complicated because modern machines are complicated, because pointers and whatever. I think that's bullshit. Sorry, this is my one swear. I think that's a very bad excuse for not having arrays with length, for having stupid type syntax, for not having a module system, for not having separate namespaces, for having separate namespaces for stuff like structs, functions like CDAs. For having a preprocessor, you should not be doing this. For having an anemic standard library, for not having nested functions. Any language can have nested functions if it wants. For not having named parameters, for not having format strings, etc. None of these features force your language into any particular designs. They are pure freebies. Take the freebies. If you're writing a language, you can just take the freebies and instantly be worlds ahead of C. Beating C is not difficult. Beating D is difficult. I don't think I've achieved it, but beating C is not difficult. Final piece of advice. I realize this is self-defeating because I want people to use my compiler and not to write their own. But honestly, my first compiler, which was also named neat, was garbage. It was just garbage. It had no syntax trees. It was using strings for everything. It had no internal consistency. It was not self-hosting. The templates didn't work half the time, no CDFE. It had no macro supports, and I didn't have any clue what I was doing. God, I love that project, though. But here's the thing. After I'd written that thing, I'd never for one moment had imposter syndrome. I never for one moment thought I wasn't cut out to be a programmer. Because, like, why are you telling me I'm not cut out to be a programmer? I've written a compiler. It has been enormously psychologically beneficial. So go out and write compilers. Thank you. Questions?
Walter immediately has something to say.
Well, writing your own language is an avenue to being a top programmer, but you're missing an essential part of it, is you got to design a gearbox too.
You went down to kind of a multi-thread, multi-core friendly design from the beginning. And I was wondering, do you have any kind of scalability numbers where you've gone up against things that would like grind D into the dust, you know, like we'd be waiting next week, you know, for the thing to come out? Do you have any scalability, you know, answers to that?
Sadly, part of the problem that kicks me here is that I don't have any big programs written in the compiler other than the compiler itself. Another thing is that it actually deeply surprised me, and this is an admission, it deeply surprised me how little multi-threading helps when you have macros. This is genuinely something that is a bit at odds. The problem is that to evaluate a macro, you need to have, it forces a break in the compiler, because the source code that you're passing after the macro is using different rules than the source code before the macro. So if you have a macro file that, for its implementation, imports another macro file, and you just pull that in, then for every single compile pass, we need to compile the compiler headers itself, at least to pass them. You need to pull those in, and then you do the macro, and then you do the next macro, and then only then can you pass your user code. The thing is, it would be possible to even optimize this, and I designed the compiler to optimize this, because what you can do is, when you have the macro object in hand, you can just load it in again. I mean, you can just restore the state of where you pass the macro very easily. You just load it from disk again. You have it in your cache anyway. And then if you know that you can do a very surface level check. You can just check that the dates haven't changed, or if you want to be fancy, that the hash hasn't changed for the compiler header plus the macro. And if you know those haven't changed, you can just load the macro again. You need to paste it. You don't even need to invoke the parser. The thing is, I don't have that implemented yet. And that's why these compiles, for instance, for the test suite are taking something like 300 milliseconds per file instead of the like 20 that they should. What I can show you is heap track traces of the compiler genuinely using 8 cores at once. Not exactly too much practical benefit, but it is happening.
Can you go back to the JSON value neat?
Yep.
Right, so in that example, JSON value is the name of the macro?
Yeah, JSON value is the syntax key that the macro uses to recognize that it's being invoked.
All right, because you define it called that, and then that returns the thing, okay.
Yeah.
Just wasn't clear to me where the macro was.
What is the runtime overhead of the sumtypes?
It's just a tag. I have
It's
not...
a fixed size tag, and then in front of the value.
Just one sec. The thing is, I have not particularly optimized this language to minimize runtime overhead. For instance, if you're looking at arrays, to correctly do reference counting in arrays, if you're doing it the normal way, the naive way rather, you just, instead of having 2 word-sized pieces of data like you do in D with pointer and length, you actually need 3, which is pointer, length, and pointer to the base of the array object in memory, so you can actually count the references there. And so what we've done with sumtypes, it's literally just a discriminated union. It's just, you have value A, you have value B, and they overlaid as a union, which, by the way, with LLVM also is very painful, because LLVM is the C++ compiler, even though they claim otherwise, and C++ does not have discriminated unions, and so LLVM really does a poor job supporting them. But then it's just an integer in front of that. And I could do a lot of micro-optimization here with like reusing bits that I know aren't used in the type, for instance. It just hasn't come up yet. But so for now, the overhead is just 1 integer.
So for the array expression, how do you know which quasi-quoting thing to use without parsing it first?
For the array, sorry?
Yeah, for the foo call on the array you showed. Your first quasi-quoting example.
Oh yeah, this one. Yeah, what was it?
Yeah. Like, how do you know that you have to use the thing on the right and not something else without parsing it?
No, I do parse it. The first, it's just that I only use the, okay, there are two different domains here. Like, I'm going to say compile time and runtime, effectively, but if you're building a compiler, that is slightly misleading. First compile time and second compile time, maybe. The thing is, if you're loading in a macro, then the macro is being compiled, and then the macro is being run in the same compile execution. So I'm going to separate those into, let's say, macro compile time and regular compile time. So since you will mostly be using those in macros. So during macro compile time, we just use the parser to effectively skip this block. Well, we kind of use it. We also pick up on these dollar expressions, so we know which variables we are interested in from the surrounding context. But largely, we just skip this entire thing. And so what we do is we just hang on to the points in the source file where we need to grab it, and we just use the parser to effectively prove that this is possible.
For sure, I get that one, but from the quasi-quoting example on the left side on the top, how do you know to use the thing on the right side?
Oh, yeah.
Some other
What's the connection between those two?
Yeah.
Right, so if you're writing a macro that actually adds its own syntax, what you're effectively doing is defining a parser rule. So in this case, because neat is using a recursive descent parser, what you do is you would just match for an opening bracket, and then you would recursively match for an expression, and then you would look for the string or the identifier for. And if you didn't find for, you would abort it and let another parse rule take precedence. And then you would look for another identifier, which would be an iterable variable. And so you would literally end up with variables. Actually, I can show you the code that does that, because we do have those.
Okay. Yeah. I think I get it now. So the the quasi-quoting list comprehension is the list comprehension itself is a concept of neat and not a concept of a macro.
No.
Quoting to okay.
No, hang on. There's actually two stages here, which is that the list comprehension is passed by a parser macro. So effectively, neat's parser lets you hook certain elements like expressions or statements, and lets you run arbitrary, though lexically scoped, additional bits of code there. And that additional bit of code can then say that the syntax for the list comprehension is something that is now recognized, or that it recognizes, and that it returns its own subclass of the parse tree class.
Okay, thanks.
All right, we're done. Program of